Okay, next question on the list is number 79. List the following carboxylic acids in order of decreasing acidity. So first off, let's just get a good definition of acidity in our head. This concept of acidity and basicity is going to come back to haunt you throughout the entirety of organic chemistry, and it's a topic that is so useful that it's almost a disservice for you to not have a really good understanding of it. If you don't have a good conceptual idea of what acidity is now, you need to make sure that that concept is really, really ingrained. The more comfortable you are with acidity and basicity, the easier everything is going to be from here on out. Okay, because everything relates to acidity and basicity in organics, just the way that it is. Okay, so let's talk about this question. So basically, acidity in the context of what we're talking about is it can be summarized as the propensity of a molecule to break or dissociate a hydrogen bond. So a covalent bond between a hydrogen and anything else, just how easily it is for that bond to be broken, that is a measure of acidity. So just how easy it is for that bond to be broken. The easier it is to break that hydrogen to whatever bond, the more acidic that compound will be, and the harder it is to break that hydrogen to whatever bond, the less acidic that compound will be. Okay? Alright, so basically what we have here are 4 carboxylic acids, and the only difference between them is just the location of these chlorines. So you'll see there are all these different permutations with the chlorine being on different locations along the carbon backbone. Okay, so we're going to use the structure to try to rationalize it out, but first let's just try to answer the question right off the bat. A concept from intro that we're revisiting for a second is Ka, or an acidity dissociation constant, equilibria constant. And basically what this number is telling you is, the bigger the number, the higher abundance there will be of the dissociated or deprotonated compound. So the bigger the number, the more deprotonated the molecule will exist at equilibrium. Okay. These numbers are pretty small, so it might not be intuitive for you to try to compare and contrast, but the idea here is that the smaller this number, the less acidic the compound is, and the bigger that number, the more acidic that compound is. Okay, so just real quick, if that's not intuitive, I'll pull up a calculator. And so what we have here is 1.52 times 10 to the minus 5. So let's just put that in decimal form just so it's easy to compare and contrast. So I'll take a 5, make it negative, 10 to that times 1.52. So we got 4 zeros, 152. Alright, so let's go ahead and draw that guy out. So we got 1, 2, 3, 4, 1, 5, 2. Okay, and same thing for these other two. So this is on the order of 10 to the negative 5. These other two will be the exact same thing. So there's no real reason to pull out the calculator. I'm just going to insert the same number of zeros and then just draw out the rest of the number. Okay, so 0.0000296, 0.0000890, or 89. Let's just say 89. And then for this guy, we have 2 orders of magnitude in between. So, I could pull out the calculator and do the whole calculation, or I can just remove 2 zeros. So this is what I'm going to do. I'll just take a 0 and remove 2 zeros, so it'll be 0.00139. So I'll do the calculation real quick, just to convince you. You can do it along if you want. So again, 3 to make it negative, 10 to that, and then multiply by 1.39, and that's going to give you 0.00139, 0.00139. Okay. So anyway, the point is that all of these, are pretty small numbers. So none of these are super acidic, but overall, there is a difference. So let's just compare, and let's try to order these from, let's say, let's do 1 is the most acidic, and let's say 4 equals the least acidic. Okay, so of these, the biggest number comes from the second compound, so this guy's going to be the most acidic right there. Okay, of these, they all have the same number of zeros, so it's no real there's no real importance in trying to compare all these zeros. It's just easier to look at these numbers right off the way. So 152, 296, 8.9. So again, the bigger the number, the more acidic. So the biggest number here is going to be this 8.9, so this guy is going to be the next in line for being the most acidic. Then we have 2.96. That's going to be next in line, a little bit less acidic, but still more acidic than this last guy. So 1.52. That's the smallest number, and it's going to be the least acidic. Okay, so we've answered the first part of the problem. So the first part's asking, just straight up, rank them by acidity. So that's the easy part. But you need to have this, conceptual idea of what exactly Ka means. So if you don't know what Ka means, or if it's difficult for you to go through this concept, make sure you revisit it at least once more. Okay. Although most of the time for organic we're going to talk about pKa's and not Ka's, but it's good to remember the difference between the two. Okay. Okay. So part B. The part B is interesting because it's asking us, how does the presence of the electronegative substituent affect the acidity? So this is actually a pretty simple question because we have three molecules with an electronegative substituent and one without. So this is a pretty easy question. What you'll see is if you look at these top three on the right, these all have an electronegative substituent. So that's going to be your chlorine. So we got a chlorine here, chlorine there, and chlorine there. So those are all electronegative, halogens. Those are going to have an electron withdrawing effect. They're going to pull electronegativity or electron density towards it, towards themselves. And we only have one example, this guy over here. This carboxylic acid has no electronegative substituent that's any different. Okay, so what you'll notice is that overall, right when you start tacking on chlorines, either here, here, or here, overall the acidity is going to start going up. So again, this guy without a chlorine, it's the least acidic. And right when you start tacking on chlorines, you're going to get this guy going up, a little bit higher, a little bit more acidic, a little bit more acidic, and the most acidic. Okay, so overall, what this is going to do is it's just going to increase acidity. That's all it's doing. Okay, so that's what we're doing once we start introducing electronegative substituents. So we're going to remove electron density and we're going to make this compound more acidic. So what you notice, or what you'll see here, is that there's really no possibility for a resonance stabilization. So the only real way that we're actually increasing acidity here is by inductive effects. So we're increasing acidity, but we're increasing acidity by induction. Okay, and we've talked about induction in class 4. Again, we will talk about it very, very soon. Okay, and again, of the two different ways we can increase, either by induction or by resonance. So we have two different possibilities. So those two possibilities are going to be resonance So those are the two possibilities, either by resonance or induction. In this case, it's induction. Later on, we'll probably do some examples of acidity effects, or how we can affect acidity by resonance. Okay, but for now, this guy is induction. Okay, so finally, the next question is going to be, how does the location of the substituent affect the acidity? Okay. Overall, this is a pretty easy question. Again, we've already narrowed it down between induction and resonance. We've said that overall, if you look at these guys, all of these chlorines are electronegative, much more electronegative than carbon. So again, they're all pulling electron density towards it via electronegativity. Okay, so that's what these little arrows mean. But what you'll notice is that there's a difference in the distance between the electronegative group and the atom, which will, result in having a negative charge. Okay, so let's go ahead and copy all these guys and pull them down a little bit. So I'll copy all these. Okay, so I'm going to take all these guys and pull them down. And basically, what we're going to talk about in class, if we haven't talked about it already, again, is that the acidity is directly correlated with how stable the resulting compound is. So let's imagine, if you will, a scenario where we've already deprotonated each one of these guys. Okay, so we've deprotonated each one, and again, this oxygen doesn't particularly like having a negative charge on it. So if you have to choose between having a negative charge and having a neutral charge, most of the time neutral is going to be the way to go. So if there's a way to stabilize that negative charge, if you can withdraw a little bit of that negative charge, you're going to stabilize the molecule as a whole, which is what's happening here. So thinking about just the proximity of this chlorine to that negative charge, it seems slightly intuitive to think about the closer that chlorine is, the better able it's going to be at removing that electron density from the oxygen. So the closer it is, the more that oxygen will feel that electron withdrawing effect. Okay, so because this chlorine is the closest, this group is going to be the most acidic. Then this molecule on the far right, it has a carbon in between it and the oxygen, so it's going to feel less of an effect. And this this chlorine in the middle, it has 2 carbons in between it and the oxygen, so it's going to feel that oxygen is going to feel even less of an effect from that chlorine. Okay, so of those, we said that the most acidic compound, I think we said that was number 1. So this is the most acidic. This is the next most acidic, and this is the third most acidic. Okay, and the formal rationale is something called proximity effects, and we should have already talked about this in class, and again, if we haven't, don't worry, we will talk about it relatively soon. But this is going to be via proximity effects. Okay, so the closer the chlorine is, the better able it is at withdrawing electronegativity or electron density. Okay, and that's pretty much it for that question. A little bit more of a conceptual question, but again, the real issue here is making sure you have a good grasp on electronegativity and how, via induction, something that's really electronegative can decrease the acidity of a compound, make it much more acidic.